All right, both eigenvalues negative. That's a sink. Yeah. When one eigenvalue is negative and one is positive, it's a saddle. And when they're both positive, C. That's a source.
That C number should be an A.
You're right.
That's just my thinking.
Yeah, that is a saddle. Yes, thank you.
100.
How'd everyone do?
Liz, you're number 1.
Okay, so we're going to talk about 3-3 today, and next class we're talking about 3-4, and for some reason I had none in the reading for Wednesday, but you should read 3-4. Fix that. I don't know why that happened.
Just check. I don't want you to hit us with a reading quiz.
Okay. Thank you for pointing it out. And then you're scheduled to have a take-home quiz that I'm going to give you Wednesday, and we do the Monday after break. I do have it with me today, and I think that you know enough to do it after this class. So I will give it to you today. That way, if you want to get it done before you leave for break, you can. Yes. Okay, so the start, a lot of today's lesson is going to be like pulling together all the stuff we learned last class, so that will be good. And then we're also going to talk about the phase portrait, how to draw a phase portrait for a linear system. Okay, so here's a linear system. I want to find the eigenvalues by solving the characteristic equation, the determinant of A minus lambda I equals 0. So the determinant of A minus lambda I. So A is the matrix 8, negative 11, 6, negative 9. Take away lambda times I, so that's the upper left and the lower right are going to end up with a minus lambda. So we've got 8 minus lambda, negative 11, 6, and negative 9 minus lambda. And we want to set that equal to 0, the determinant. To calculate the determinant of a 2x2 matrix, you just multiply AD minus BC, upper left times lower right. Minus upper right times lower left. Set it equal to 0, yep. And then this is going to end up being quadratic, so I'm going to have to FOIL, combine like terms, and like have my fingers crossed the whole time that it'll factor. And it will. Yeah, so this comes out to negative 72. Minus 8 lambda plus 9 lambda is plus lambda squared. And that's going to be plus 66 equals 0. Simplify and I get lambda squared plus lambda minus 6 equals 0, and that'll factor. Okay, so that's lambda plus 3, lambda minus 2, 0.
Wouldn't it be minus 3 plus? No, because it's plus lambda.
No, because it's plus lambda.
Oh, I got minus.
Oh, you did? Did I mess up?
No.
Yeah, because it's minus 8 lambda plus 9 lambda. Yeah. All right, so my eigenvalues, you said each factor equal to 0, right? And you end up with lambda is negative 3 or 2, right? So I have 2 eigenvalues, negative 3 and 2. I want to compute an eigenvector for each one of those. So I have to solve the equation AV equals lambda V twice, once for each lambda. So let's see, break that in half, and I want to solve AV equals lambda V using lambda is negative 3. So A was 8, negative 11, 6, negative 9, times some vector, my eigenvector, which is what I'm looking for.
We just multiply that by 2. That's my equation of different things.
That's
I'll
fine.
just do the dxdt rather than go through the matrix. Do dxdt, dy dt, and then the spectrum.
Okay. All right, so when you're solving for eigenvectors, the left side of, so basically this matrix equation is equivalent to two equations with two unknowns. There's always infinite solutions, which means either when you translate this to two equations, you either are going to get one equation that tells you no information whatsoever, or your two equations are going to be multiples of each other. That way you'll have infinite solutions. So just to remind you how it works, you dot product each row with each column, and that gives you the first component, or your first equation. So I'm going to have 8x minus 11y is negative 3x. That's one equation. And then my other equation is going to be 6x minus 9y equals negative 3y.
They're not multiples of each other.
They're not multiples of each other.
But that's fine. That's fine. You can just use common sense.
Or substitute, actually.
No, you don't.
X equals
It's just
Y.
Plus 11y. Just you have 11x equals 11y. It's just 9. Yeah.
Yeah.
6x equals 6y. Just like
Yeah, they are multiples of each other. Yeah. So if you solve, this ends up being 11x equals 11y, right? Or x equals y.
Yeah.
This one simplifies to 6x equals 6y. So these are equivalent equations, right?
Y.
So x equals y. So I need to, any vector where x equals y is an eigenvector for this guy. So we'll use 1, 1. Will be the easiest. Then I just do the whole process over again, but use lambda equals 2 to get the eigenvector that goes with lambda equals 2. Okay, so I've got 8, negative 11, 6, negative 9, times the unknown eigenvector equals 2 times the eigenvector. So I have 8x minus 11y equals 2x, and 6x minus 9y equals 2y. This ends up being 6x equals 11y. This ends up being 6x equals 11y. So my two equations are totally equivalent to each other. And any vector xy that satisfies the equation 6x equals 11y is an eigenvector.
11, 6.
11, 6. So if x is 11, y would be 6, because then 6 times 11 is 66, 11 times 6 is 66, so I satisfied the equation. Any multiple of 11, 6 would also work. So there's my eigenvector there. All right, so the purpose of finding eigenvalues and eigenvectors is that you can use them to write the straight line solutions to a linear system. So each eigenvalue and associated eigenvector, we can put them together in the form e to the lambda tv to form the straight line solutions. So one straight line solution would be y1, which the y with the arrow over it is just a way of saying a solution x1, y1 all together. So x1, y1, that is going to be e to the lambda 1t. So my first lambda is negative 3. So it's going to be e to the negative 3t times my associated eigenvector 1, 1. And you can either leave it like this, or you can distribute that e to the negative 3t to both terms of both components of your vector. So this would be e to the negative 3t, e to the negative 3t. I don't care which way you write it. Often in the answers, I've been putting it both ways, because you can write it either way. So whichever one you feel comfortable with. Okay, so that's one of my straight line solutions. And then my other straight line solution is my other eigenvalue and eigenvector. So this is just x2, y2. Put them together, e to the lambda t. In this case, lambda is 2. V, and v is the associated eigenvector, which is 11, 6. And distribute or don't distribute, whichever you want. So you get 11 e to the 2t and 6 e to the 2t. So you get two straight line solutions. All right, so I want to check that those two solutions are linearly independent. That just means plug 0 into both of them and make sure the resulting vectors are linearly independent, so not multiples of each other. So I just need to know y1 of 0. So if I go back here to y1, make my t's zeros, and I get 1, 1. In y2, if I make my t's zeros, I get 11, 6. So I have 1, 1, and 11, 6. Okay, are those two vectors multiples of each other? No, so these are linearly independent. So that's important to be able to get the general solution, right? If you have two solutions, you can, if they're linearly independent, you can just take a linear combination of them, and that's the general solution. In general, when you get two distinct eigenvalues, if you're solving for eigenvalues and you get two different numbers, they'll always produce two linearly independent solutions. So after today, you don't have to check this. You can assume that it'll always work.
That means if you're given eigenvectors and we have,
What's that?
that means if you're given eigenvalues and we have to see if they're linear independent, you can solve for those ones, right?
Right. Right. If you solve for them and you get two different values, sometimes you can get a repeated value, like when you solve a quadratic and you get x equals 3, but multiplicity 2, there's only one solution. In that case, they're not linearly independent. But if you get two different eigenvalues, you can always assume they're linearly independent.
I remember that.
So now that I know I have two linearly independent solutions, I can write the general solution, which is just k1 y1 plus k2 y2. So y of t, which just means x of t, y of t. And you don't have to write this both ways every time. I'm just trying to really reinforce it so that you won't forget what that means. Okay, so this is k1 times y1, and y1 was e to the negative 3t, e to the negative 3t, plus k2, y2, which was 11 e to the 2t, and 6 e to the 2t.
So from now on, we can always assume that we have an initial value problem when we solve them for k1 and 2.
Yeah, if you have an initial value problem, you're solving for k1 and k2. Yeah. I haven't given you any initial values yet, right? But we have the general solution now. Before I give you an initial value, which we are going to do in a couple minutes, first I want to look at the vector field, or the direction field. And I want to sketch some solutions that correspond to various initial conditions. So again, this is x and y. Can't really see time in here. But I want to draw the straight line solutions with their directions. Okay, so my straight line solutions were 1, 1. So you can see that in the picture here. The line y equals x along the vector 1, 1 is a straight line.
Pointing towards the origin.
Pointing towards the origin. How could I have known that without the direction field?
Values.
The eigenvalue that went with that straight line solution was negative 3.
Yeah.
Negative eigenvalues have solutions that point at the origin. So let's label this one lambda equals negative 3, so we don't forget. The other straight line solution is 11, 6. So let's see, if I plot 11, 6, I'm supposed to get a straight line solution. So I think it's like 11, 6. Looks kind of like this.
So this is a stable saddle? Can't draw.
Yeah, and the arrows are pointing out on this one. That's just a habit. Arrows are pointing away from the origin because that one corresponded to lambda equals 2. And then if I were going to use the direction field to sketch several other solutions, I would create a phase portrait. And then you can just pick any random spots you want, and they tend to kind of follow the straight line solutions. You know they won't cross. You know they won't cross the straight lines because of uniqueness. So we've got solutions that look kind of like this. Then we've got solutions that look kind of like this. Yeah, and in between, in the like skinnier part, they kind of go like this. They kind of look like hyperbolas, I guess. So that's what the phase portrait looks like. It turns out that this phase portrait is typical whenever you have one negative and one positive eigenvalue. When the solutions around the equilibrium point look like that, we call this a saddle.
I have a question about the uniqueness there.
Yeah.
Doesn't this contradict that? You know, is that the equilibrium? Oh, no, they're all in the same equilibrium point is what it is, right? You know, that we're saying that's all towards the origin?
Right.
Okay. Because I was going to say, like, the two functions or the two...
Yeah, these actually don't cross at the origin because the solutions along this straight line solution for lambda equals -3 approach the origin but never get there. It's asymptotic. So they actually don't cross this other one.
So the equilibrium points are crosses, but they do have points of intersection, is what I'm saying.
So when I'm drawing, typically we translate a phase portrait into a T and then an X graph or a Y graph, and those are the solutions that we never see cross. Yeah.
Okay.
Yeah. Okay, so the last thing I want to do here is find the particular solution that satisfies the initial condition y of 0 is 0, -5. So that y is bold, which means it's a vector, right? Which means that actually says x of 0 is 0, y of 0 is -5. So let's just copy down the general solution, and then we'll solve for K1 and K2. Okay, so I know that x of 0 is 0. So x of 0 that means x is the first component of this vector. So I want to plug zeros in for t into the top part of my vector, the first component. So I get e to the 0 here, so I get k1 times 1 plus k2 times 11 times 1, which is 11 k2. And that's supposed to come out to 0. And then y of 0, that y is the second component of my vector. So I'm just going to read off the second components. So I have, when I plug in a 0 for t, so I have k1 plus 6k2, and that's supposed to be -5. So I have two equations with two unknowns. You can use your favorite method to solve this. You can you could set up a matrix. You could row reduce it. You can use technology. You can use substitution or elimination.
So is it always going to be e to the something t?
Yeah, because that's how we build the straight line solutions. It's always e to the lambda t v1
So pretty much it's always going to be k1 k2 times cosine. Like that is 0. That always going to equal 1.
It's like,
It's always going to be either 0, right?
she wrote it right there.
Yeah. Yep.
Does that relate to the factor of integration? Is that the reason why it's always e lambda t? Because when we
Oh, I don't know. It's a good question.
because when you think about it,
Yeah. Because that was for linear.
homogeneous.
Yeah. I'll have to think about it. I'm not sure.
Mr. Riley.
All right, so let's finish solving this. I'm going to do a quick elimination because I've got K1 in both equations. I'm just going to write the first equation under the other, subtract them. 6 minus 11 is -5, K2 is -5, so K2 has to be 1. So K1 is equal to plus K1 plus 11 is 0, so K1 is -11.
Yeah.
Okay, be careful to not just circle your K1 and K2 and call it done, right? The question was to find the particular solution, so you have to rewrite that whole thing, replacing K1 and K2 with your values. So we're going to have y equals -11 e to the -3t e to the -3t plus 1 times 11 e to the 2t, 6 e to the 2t. And again, distribute or don't distribute these values of K1 and K2, I don't care. Doesn't matter. Alright, so you might remember from your reading that there are 3 kinds of phase portraits in this section: saddles, sinks, and sources. We just did one example of a saddle, right? So in your activities, I gave you an example to work through that's a sink and that's a source. And so make sure that you work through all of it so that you can see the typical phase portraits for sinks and sources.
Why is it called a saddle and not a saddle?
I think just because the picture kind of looks like a saddle. It's like, it like goes up and one, like, yeah.